Okay, class. I've just walked out of Tuesday's class and I'm back in the office here. And so we're going to continue on so that uh, we can get something posted for class on Thursday. So this is where we left off. We were looking at cold weather operating tips to de-ice your cooling tower if it happens to get iced up. So I think we went through most of this, but we can hit it one more time. The first thing would be to just cycle the fans off. That warm water, you probably got 50, 60, 70, 80 degree water, something like that, maybe even hotter, being introduced at the top of the tower. That falls down the fill, hopefully on the outside, preferentially, we would like, and can melt any ice buildup in hopefully a fairly short period of time. So that would be option one. If that doesn't work, then we should go through a de-ice procedure, something like this, turn the fans off and wait for the rotation to stop, run the fan in reverse for 2 to 5 minutes at low speed, approximately 30%, cycle the fan off, wait for it to stop. Hopefully the ice is now melted and we can resume operation. What this does is it pulls the cold air in the top of the fan. It goes the opposite way from the inside to the out through the fill. So the air has warmed up significantly by interacting with the water that's falling down across the fill. And so when that air gets to the ice, it's warm enough to melt it. Resume operation, monitor and repeat as needed. Don't let it get too bad. It's better to catch it early. Okay, some options to consider. We can get a basin heater package. So that basin, if it's cold enough, weather can actually freeze up. So it could be strip heat. It could actually be from some other heat source if you wanted to. But usually sized to maintain 40 degrees in the basin. Like I said, it could be electric, steam, or hot water. And we have thermostatic controls so that it doesn't just run all the time. It only runs when it's trying to get below 40. We could have a remote sump. The tower could set up on the roof, and the sump could actually be inside. You see plants that just have big tanks inside that serve as the sump to the cooling tower. So the pump returns the water up on top, and it falls down through the tower, and then it's piped back into the sump or the tank inside. So that's, as long as you condition the building inside, that's pretty much hard to freeze up. Again, you can freeze up the tower, but you're not going to freeze up the sump. So that's a pretty good idea. Okay, wrap up. We're just about finished this. Variable flow offers big energy and dollar savings potential. Fan energy varies, not really quite with the cube of the speed, but pretty close. Inherent differences between cross-flow and counterflow tower. Counterflow, it's hard to modify much in terms of water flow rates. The cross-flow, it works pretty well on. So probably the good thing to do in a real-world situation would be to talk to the cooling tower sales rep or engineering reps to get a good handle on what you can really do. These were the questions that we were attempting to answer, so hopefully we have done that, or at least shed some light on those topics. Additional, and we're done. All right, so I'm gonna get out of this presentation, shut it down. Okay. So this is the one I forgot to hand out, but I will make sure this is emailed out to you, and I will hand it out. This is not very long, but it has some really good information on water use in cooling towers. And so I'm going to go through this. I think I'll make it even one bigger. Whoops. See if this will work. Yeah, that's pretty good. Okay, so we start off with We have three different uses of water in cooling towers, and the first would be evaporation, and that's the whole point of the tower, is to promote evaporation, to cool the water stream, the heated water stream coming in, so we can drop 10, 15 degrees out of it and return it to a chiller or some sort of an industrial process. We should note that this evaporated water contains no minerals, so it should be pretty pure when it evaporates. It leaves all that stuff behind. The second method would be loss and drift and splash out. So that's water that, you know, just the air blowing through the tower carries droplets out of the cooling tower. That's water that is recirculating through this cooling loop, and it contains minerals, chemicals, bacteria, all the crud that's in the recirculating water, and that gets carried off because it's not evaporated. These are droplets that get carried away. It's pretty much an uncontrolled loss, listed as a percent of tower recirculating flow. We do have drift eliminators, or you know, they're called eliminators, but they don't totally eliminate it, but they will reduce it. So it varies, and we list this 0.008% as a reasonable number for a new tower in good mechanical condition. And that's a percent, not a fraction. So we got to add 2 more decimals to that before we multiply. And the third method is blowdown. Some people call it bleed flow, where in order to control the concentrations of minerals, chemicals, bacteria, that sort of thing, we intentionally drain some water from the tower, put it down the sewer, and then make it up with fresh water. That still has a little bit of at least the minerals and probably chemicals, hopefully no bacteria when it first comes in, to maintain the water inventory at the appropriate level. This is often done automatically with a conductivity. So we measure the electrical conductivity of the water. That's a surrogate for the mineral content. And then that can automatically control a valve, which will open and close to maintain a certain conductivity setting. And there are other ways to do it as well. Okay. So we're going to move on to point 2 here, water use by evaporation. So we remember that a ton of cooling is, a ton is a rate of energy transfer. So it's 12,000 BTUs per hour. And usually in a chiller, we're removing it from water. Mechanical chiller adds roughly 3,000 BTUs per hour of parasitic load. And so what this is looking at is that's roughly a kW per ton into the compressor. And so a kW is 3,412 BTUs per hour. So we're saying if it's a kW per ton, we get about 3,000 BTUs an hour of energy added to the refrigerant in the compressor that has to be cooled away by the condenser water. So thus, for every ton of cooling in the evaporator, the condenser actually has to reject 15,000 BTUs of heat. So a cooling tower ton is 15,000 BTUs per hour on a centrifugal or reciprocating chiller. We see this footnote 1. If we go down here, it says absorption chiller has a much greater parasitic heat load. For each ton of chilled water produced, absorption generates 18,000, and that 18 plus 12 is 30,000 BTUs per ton that have to be rejected. And so one rule of thumb, this is not what the carrier program defaults to. And when you run your homework, I would go ahead and accept the carrier program default. I think it's 3.75. But anyway, this article says that the condenser water flow on an absorption unit is 4 GPM per ton, sized at a 15-degree delta T. I think the 15-degree looks right. And this is relatively right. So Okay, so rule of thumb one, 3 GPM of condenser water per ton of cooling with a 10-degree delta T. So that's our kind of standard number that we've been working with. This, if you do 500 GPM delta T on that will come out to 15,000 BTUs of heat removed from the system in 1 hour for each ton, a ton being 15,000 BTUs, or a ton hour being 15,000 BTUs. Okay, so this just shows the calculation. 3 GPM times 60, that's gallons per minute. So we get the minutes out of there, 60 minutes per hour times the weight or mass of 1 gallon of water, 8.337 here. And the specific heat is 1 BTU per pound mass per degree Fahrenheit times 10 degrees Fahrenheit. That gives the 15,000 BTUs per hour per 1 ton of refrigeration. Okay. Rule of thumb 2, 1.8 gallons per hour of evaporation per ton of cooling. 1.8 gallons per hour for every ton of cooling. So evaporation, so we use this nominal number here, evaporating or condensing a pound of steam or evaporating a pound of water is nominally 1,000 BTUs. If pressure goes up, this goes down some, but anyway, this all happens at atmospheric pressure. So that's pretty close. That's a good number. So evaporating this 1.8 gallons requires 15,000 BTUs of heat, as shown by equation 2. And so if you take the 15,000 BTUs an hour, which would be 1 ton, and divide it by 1,000 BTUs per pound, and then divide by 8.33 to convert into gallons, we get 1.8 gallons per hour. So that's interesting. So we can use that given the tonnage. I mean, like on this homework, of say if we're doing a 300 ton chiller, then it's pretty easy to figure out roughly how much water is going to be evaporated in a month if it operates at full. So you have to assume what percent load it's going to operate at. Okay. Moving on, water used by drift. Drift is the uncontrolled blowing of water droplets. And we said a new tower in good condition would lose 0.008%. And so we do a little math on this. The water loss per ton of cooling in 1 hour or per ton hour would be 0.0144 gallons per hour. So this is not a whole lot of water. However, if you run the math on, say, a 500-ton tower operating around the clock, it turns into a fairly large amount of uncontrolled, chemically contaminated water. So this has the bacteria and the chemicals and the minerals and all that stuff in it. Now, when you go through this number is incorrect. This 0.018. This should be 0.0144. So this number here should be right here. And if you check the math, it works. The math is correct if this number is substituted in for this one. So there's just a little typo here. But so in a month, if it operated full out at 500 tons, this chiller would evaporate, or I'm sorry, not evaporate, but it would, this drift would be over 5,000 gallons per month. And then the evaporation is on top of that. So the rule of thumb for drift is that it will amount to 10 gallons per month per ton that operates for that entire month. So we had 500 tons for the entire month times 10 would be 5,000. A little bit better number, it might be 5,184, but it's pretty close. Spills, leaks can also contribute. Okay. Let's move on here. Item 4, water use by blowdown. And of course, we said this is the intentional draining of this mineral bacteria-laden water from the cooling tower system. It's quantified. We use the term cycles of concentration, or sometimes just cycles. And it's equal to the ratio of the makeup water volume to the blowdown volume, assuming that spills and drifts are negligible or you've included it, whichever. Cycles can be calculated by the ratio of the concentration of a soluble mineral, chloride or some other mineral, in the recirculating water to the concentration of that mineral in the incoming water. So if the mineral was twice as concentrated in the recirculating water as the makeup water, the tower would be running at 2 cycles of concentration. If the mineral were 4 times as concentrated, the tower would be running at 4 cycles. So here's some equations all kind of summarized together. So the makeup water is the evaporated water plus the blowdown, and in that we've included any other losses from the tower. They're just kind of grouped in there together. Okay. The cycles, we can calculate it as the volume of makeup water divided by the volume of blowdown. We could also do it, it could be chloride concentration or some other species. It doesn't have to be chloride. So we just, we measure those concentrations in the blowdown and makeup water, and we calculate cycles. And also the blowdown volume is the evaporation volume divided by the cycles minus 1. You do a little algebra on this, you can come up with that. Okay. So amount of water evaporated by the cooling tower is a function of the load on the system. Water loss through drift and spillage is a function of the tower design and how it's operating. It is the amount of blowdown that can be affected by water treatment. So if we clean up the water better, then we don't have to blow down so much. So if we purify it more, or put more additives in there to keep, say, bacteria or mineral concentration down, then we don't have to blow down so much. Let's see. So water used in gallons per hour for a 100-ton cooling tower at different cycles are shown here. So once through means that we're buying city water, or I guess we could take it out of a creek or whatever, but we're getting water and we just run it through the chiller or the heat exchanger, and then it gets heated up and we throw it back in the creek. So we don't have a cooling tower. It's a once through cooling situation. So, everything comes in, everything goes out. And so we're showing 18,000 gallons per hour. So if we're running 1.2 cycles of concentration, then the evaporation is 180. The evaporation is going to be the same for the same 100 tons of cooling capacity, because it's 1.8 per ton. So 1.8 times 100 is 180. Then the blowdown is at 1.2 cycles is 900, and the 900 plus 180 is 1080. And so you see, if we can run more cycles, which is less blowdown, you see the blowdown flow going down. This would be the cycles. Then you see the makeup water goes way down. And we accomplish that by doing better cleanup on the water that's introduced to the tower. Note that as cycles of concentration increase, total makeup water usage approaches the evaporation. Also, increasing cycles of concentration at higher cycles gives less water savings. If you're already operating say you're operating at 6 and you go to 7, well, that only saves what, 6 GPM. If you're operating at 2 and you go to 3, that saves 90 GPM. So it depends where you are as far as how many cycles you're running. If you improve by 1 or 2 cycles, how much water you're going to save. Okay. And so this is just a plot of that information. So it shows the blowdown plus evaporation and then just the evaporation. Okay. So I'm going to hold up here and reload here for just a second. So we'll pause recording. Okay. So we're now going to shift gears completely. And this is starting the next block of the course. The first block was chillers, cooling towers, associated carrier program simulations. And now we're going to go into basically hydronic systems. This is the first document I'm going to talk of a little bit. And this has been emailed out to you. And so you have a copy and you also have the electronic version. So this is Bell and Gossett material. They do an excellent job putting out materials and doing training for the HVAC industry. So what we're looking at here is just some general classifications of hydronic system. Let me make this 1 tab bigger, a little bit easier to see. Maybe 2 tabs bigger. There we go. So you can identify a hydronic system as either closed or open, and a piping arrangement as direct or reverse return, or can be a combination. So we're going to go through some of this. So open piping system is one in which part of the piping or circuitry contains a reservoir that's open, such as a cooling tower, and often there is an elevation change from where water is discharged from where it originates as it goes through this system. And probably the cooling tower, this for an open type system, is a good example. So, you know, we have this as, this would be the basin on the tower. So this is flooded with water, and this would be the surface, the top surface of that water. And so when the pump operates, it draws water from that basin, and this is the elevation level of reference, which is the surface, and the water flows into the pump. Say it gets pumped through a heat exchanger or gets pumped wherever, and then comes back out, picks up energy, comes to the back top of the cooling tower where it is sprayed out. And so we have a break. So there's no pipe from here to here. The water is falling down. So this is considered an open system. And this elevation from where the water comes out of the piping system up here to this free surface is called a static head. And so that's, it doesn't matter what the flow rate through the system is, the pump always has to overcome, the pump can't overcome the static head, then there can be no flow. If it's not strong enough to push water up, if that's, say that's 30 feet, if you only have 20 feet of head developed by the pump, there's no way. It's not strong enough to take it from that level and push it up there, you'll have no flow. Then the rest of the pump head is caused by friction. There's frictional loss. We have an entrance loss. We have piping losses. We have an elbow loss. We have more piping, another elbow, more piping. We come into the pump, come out of the pump. We have friction here, an elbow. We have the condenser pressure drop, all of this up to here. So the pump has to overcome at whatever flow rate it's pushing, not only the static head, but the frictional head as well. Okay, let's see what they say here. And this head can actually be negative. In this case, you know, we could, not necessarily in a cooling tower, but we could have a tank up here that we're pulling out of, and then this could go to a tank that's down here someplace, in which case that static difference would be helping the pump instead of making the pump supply it. So the static head can be plus, minus, or zero on this. Okay. Closed piping systems is one that's completely sealed. In other words, it's encased in pipe all the way around. And so there, on these, it's only friction losses in fittings and components. There's no static head to worry with. So it's a significant difference between these two types of systems. So this could be an example of a closed system. So the boiler, everything is encased in piping and components. We come out of the boiler, all of this go through coils, piping, return. So it just pumps around in a circle. There's no break in the system where we have to, basically the pump has to pick water up from this level and put it up here. So this would be an example of the closed piping system. Okay. Now let's talk about direct return piping. So you see here we have what we would call probably 3 zones, or it could be 3 terminal units in the same zone. It doesn't, we're not showing controls yet, so you don't know, is there one thermostat controlling all 3 of these, or does each one have its own thermostat? We don't know, and that's not the purpose of this discussion, so we're not worrying about it. So anyway, we pull hot water out of the boiler, we pump it up to this point, and so we come out here and we branch up to the coil on some sort of a terminal. This could be a radiator, or it could be a hot water coil and an air handling unit. We come back out of that, we go down to the return, and then we go right back to the boiler. So you see, this is called direct return because this closest unit has the shortest supply piping. If you go, say, from the boiler, all of the 3 circuits have some of this in common from here to here, but then I have a short pipe up to the unit, through the coil, down a short pipe, and the shortest return path. So this is called direct return. If I look at the furthest unit, it comes out and it has, here's the common piping to here. We split off some here, the rest of it goes down, we split off some more here, and then the rest of it has to go all the way down here, so it has the longest supply path, and guess what? It also has the longest return path all the way back. So as far as pumping head is concerned, it's going to take, if the flows are equal, it's going to take much more pumping pressure developed to force the same flow rate from this point all the way down to here through the coil and all the way back as compared to the other 2 circuits. But so short down, short back, long down, long back, that's a characteristic of a direct return system. And when we see a reverse return, then it'll become even clearer. Let's see, what other comments? He says if terminal units have widely varying pressure drops, or if throttling type control valves are used to control flow rates, it's generally advisable to use direct return. So if these coils have widely varying flow pressure drops, then it's okay to do this. This saves pipe. We have less pipe compared to the reverse return. So let's look at reverse return here. So we're coming out of the boiler, and this goes to my shortest supply path, but then I come out and look, so my return then goes all the way down here to the end. Now it has picked up all of the flows, but returning, and then all the way back down here. So what this does is it tends to equalize the length of the flow path from considering the supply and the return. So, we have a short path here, but we have a very long path on the return. We have kind of an intermediate path here, and we have an intermediate path on the return. And I have a long supply pipe, but relatively short on the return. So that's what the return or reverse return system does. Designers should attempt to select all terminal units with equal near equal pressure drops if reverse return arrangement is used. The idea here, this will be somewhat self-balancing. If these have the same pressure drop, they have approximately the same path length. And if these are also equal pressure drops, then you turn this thing on, you won't have much trouble balancing, getting the proper flow to each of the coils. Up here, if these coils all have the same pressure drop, you're going to have to use a balancing valve to put extra resistance in this short path, or it will get most of the flow, and this poor guy out here on the end won't get anything. And so that's really the benefit. It makes it easier to balance this, but you have to buy more pipe. On this guy, it's harder to balance at times, but you buy less pipe. So that's kind of the way that goes. Okay. This would be a, let me make that just one smaller. This would be a direct reverse combination. So let's see, this is a reverse return header with direct return risers. So the header, the main distribution piping, is reverse return, because here's our short going up into this, this riser. And then when we come back out of the riser, we go all the way down here and all the way back. So that's definitely reverse return. The furthest riser, we come all the way down here, up through the coils down, and then relatively short return. And this one's intermediate. So that's reverse return on the header, but the risers are direct return. So we go up short path down, long path up, long path down. So, you know, and there's guidelines, and, you know, I mean, there's all kinds of possibilities in doing this sort of thing. It says required terminal unit flow rates will be maintained to plus or minus 10% of design if the riser pressure drop combined supply and return does not exceed 50% of the terminal unit pressure drop. So the riser pressure drop, supply and return, would be the pressure drop here to here on this pipe, and pressure drop here to here compared to the coil pressure drop. Okay. We have situations where we can do one pipe systems, where we come out, we go through radiation, a coil, something like that. This could be a baseboard radiator. And what happens is, as we take heat out of this thing, the temperature simply falls. We might be 200 here, maybe 190 here, 180, 170, 160 before it goes back to the boiler. And of course, the sizing of the units has to be taken into consideration to get the appropriate amount of heat out. So that's a series loop. You can do it like this. This is a trade name, these monoflow fittings. They will adjust the amount of flow here. It will take out a certain amount here, put it in and mix it, take out a certain amount here, etc. So that's a way to adjust the amount of flow that goes through each coil instead of putting all of the flow through the coil. You know, one pipe system, small buildings, sub-circuits, that's generally speaking, you don't see a lot of that. I'll let you read through some of this. Two pipe systems, and there's three pipe systems. Let's see, two pipe distribution system, separate supply return mains, widely used all systems. Typical two pipes are illustrated in figures 1, 2, 3, and 4. So these are all two pipe. Okay, what do we have here? Three pipe systems. This, you don't see this anymore. This is where you could have a heating pump, a chiller pump. So the heating pump is taking hot water, circulating it up to the terminal unit. The chiller would run the chill water pump, and then this valve would decide which it was going to select, and then it would return all of the water. It would mix it and return it together. But we don't do that because you might have a unit heating, cooling. You want to preserve that return water temperature. On the boiler side, you want to keep it as warm as possible, and on the chiller side, you want to keep it as cool as possible. So this you really don't see anymore. In the 4-pipe systems, this simply means that each air handler or terminal unit has the ability to receive either hot water or chill water at the discretion of its controls. So we're showing a 3-way valve here. Let's see, I've got my boiler, my hot water coming up here. This thing is, it's confusing as I'll get out. Okay, and then so we can feed hot water into the terminal unit, or we can feed chill water into the terminal unit, and they should return separately either to the chiller or boiler. That's that's a little confusing, but that's what it's getting at. Okay, we have primary, secondary systems, and we'll spend a bunch of time going through this, so I'm not going to stress it too much right now. You should read through here, but basically what this works is we have one, say on the boiler, we have a central distribution loop that is carrying hot water. So this would be the primary. It's coming out here, going down and coming back. And then we have secondaries, which could be, it could be a whole building or it could be a separate room. And when the secondary pump here runs, it pulls water out of this primary loop and can pump it through this secondary for heating and then return it back to the boiler. Likewise, or if we don't run this pump, we can run a pump over here and we can put chill water up into this loop as well. And we could still use this pump to circulate. So this secondary zone can heat or cool because of the chiller. This is a heating only. And again, this pump runs, it pulls hot water out of the primary loop through the secondary and then returns it. This could be underfloor or radiant panel, and this could be domestic hot water. So we're going to spend a bunch of time on that. I'm not going to spend too much on it right now. And then this is radiant panel systems. There's different ways to pipe them up. This one, you see, if you have hot water coming in here, the water cools down continuously as it goes through here. So this guy over here is going to get much colder water than this guy over here, and that may cause a problem. Okay, so you can supply to like a header situation where we have our hot water coming in here and we pull off a little bit. So each one of these crossing pipes gets the same temperature of water because, you know, this is our main water. It comes up and then it all goes through this way and then returns. You've got serpentine, grid coils. You got all kinds of options for this. So at this point, we just want to kind of get used to the nomenclature. So please read this carefully. And this is just the starting of our discussion of hydronic systems. So I think that's going to wrap it up. I will get this posted. Please do this. You have the hot gas bypass article that we're going to have a little quiz on when I get back. And then you have actually 2 homeworks, one to finish and a new one to start on. So you should be pretty busy for this next week. So I will see you next Tuesday. So hope you have a great week. Thanks.